This is my fifth video on analyzing graphs of functions in which we're going to look in on average rate of change of a graph. Okay, and the first thing that I kind of want to indicate is this. If we were to look at, say, some graph of an independent and dependent variable, maybe this is time flowing and this is, say, distance over time, we could say that what if I were to have my car in cruise control here at the same speed the entire time? You would notice that my distance would be changing the same way per units of time. So when we talk about average rate of change, this would be things like miles per hour, like for example, that would be distance over time, okay? What we're really looking at is the slope of the graph. We're looking at how far our distance changes with respect to a given interval of time. So when we do this, what we're really looking at is two sets of, say in this case, times. And what we're looking at here is two sets of distances, maybe distance 1 and distance 2. So in order to find the average rate of change, this would be really easy to do. Finding the slope of this graph, recall that slope is just rise over run, okay? And in this case, we would say, well, how far did this graph rise? An easy way to do this would say, well, the change in distance would be d2 minus d1, where the change in time here would be t2 minus t1 would be this distance here, okay? So we would say t2 minus t1. The thing I really want to point out, though, is that when we talk about rate of change of a graph, we are looking at the slope of a graph. Now, this situation that I've generated here is a very much linear situation. If I had gone back and said, well, this isn't a cruise control situation. Maybe I say time and then distance is a function of time. Maybe I started off really slow and then I started to accelerate and then I slow down and I get to my destination maybe and I have an endpoint here. But let's say between, say, time 1 here and time 2 here, what I'm really interested in doing is finding the average rate of change of my graph. The way we can do this is we could say, well, still what I'm going to want to know here is what distance was I at here? We'd say this is, say, distance 1 and it occurred at time 1. And what distance was I at here, which we'll call this, say, distance 2. And that occurred at time 2, d of t2. But what we'll do is instead we'll find the slope of what we call the secant line that passes through these 2 points. And this secant line, its slope would be tantamount to the average rate of change over some given interval of time or given period of input values, okay? So in order to find the average rate of change, we'll define it as the slope of a secant line of a function. Remember that a secant line intersects a function at 2 points, but the slope of the secant line represents the average rate of change between those 2 points over a given interval of inputs. Okay, so we're looking at just a set interval of, say, input values or x values. So we define our average rate of change as being this. And you'll notice that I've written a little bit differently here, but we say given some interval of x values, maybe x1 to x2 instead of times here, we say that it's rise over run. So we'd say the run here would be this x2 minus x1 distance. That would be that distance here between these 2 points, and that would be considered our run. So you'll notice that this is really just our run expression here, whereas up here we say that f of x2, well, that's really the y value at x2 here, and then this is the y value at x1, f of x1. So we say that distance there would just be f of x2, that y value minus this y value here. That would be considered our rise. Okay, so this top expression really is just our rise. What I would like to do in this video is just kind of use this expression for slope of the secant line to find the average rate of change of a graph. So what I've done is I've given this function here, this second degree function, this quadratic, which is going to be the graph of a parabola, and of course we know leading coefficient positive means it's going to open up, but I want to know what is the average slope or average rate of change of this graph over the interval from x equals 1 to x equals 5, okay? So what we can do is we can start by saying, well, the average rate of change is defined as being f of x2 minus f of x1, our rise over our run, x2 minus x1. So since we have these two x values, what I'm going to do is I'm going to rewrite this expression this time. We're going to say, well, really what it is, it's our y value at x2, which is going to be the y value when x equals 5, minus the y value when x equals 1. And this is all going to be over 5 minus 1. So in terms of evaluating this, the bottom is pretty straightforward to evaluate. The interval is 4 units of length long. But the top here, f of 5 and f of 1, we're actually going to need to determine these. So very easy to do. We'll go ahead and start by plugging 5 into our function. We say 5 squared minus 2 times 5 plus 8. This would, when evaluated, give us an expression that says 25 minus 10 plus 8. And going through our order of operations here, we'd say that this right here is 15 plus 8. So we get a value of 23. So f of 5 is equal to 23. That is our y value when x is equal to 5. And we say, well, what is f of 1? And again, we'll just go ahead and plug that input value into our function here. Say plus 8. We get 1 squared is 1. Minus 2 times 1 is 2 plus 8. And 1 minus 2, of course, is negative 1 plus 8. So we get a value of 7. So we say 23 minus 7. What do we get with that? Well, that would be 16. So we get 16 over 4. In other words, we would say that the average rate of change, or the slope of the secant line, would be equal to 4, or positive 4. It's increasing at an average rate of 4. So what I would like to do now, as a matter of fact, I went ahead and I put this function in to GeoGebra here, and you'll notice it says x squared minus 2x plus 8. Here's our parabola, and down here I've already highlighted a couple of points, but you'll notice that when I hover my mouse here, we say that this is the point on the graph 1 comma f of 1, or 1 and then the y value 1, and you notice that the y value is 7, like we confirmed. And also that if I go over 5 and say, what is our function value at 5? We plugged in 5 and we notice that it's at a height of 23. So essentially what I would like to do is graphically interpret the average rate of change. And what we're going to do that is I'm going to say, well, what if I connected these 2 points right here? And I am going to change this so that we can see it a little bit better here. We'll change it so that it's thicker, and maybe we'll go with like an orange color. Oh, orange, instead of orange. But we say, well, what is the slope of this line? Well, this is easy to confirm. We could count rise over run, and I notice here that we calculated that the rise over run was 4. And so I noticed that there's also a point on this line at a convenient point there, and we can say that it goes up 1, 2, 3, 4, and then over 1. If we wanted to do all of the rise over run that we just calculated, though, we would say that it goes from 7 up to 23. And that is a distance of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, whereas it ran 4 on that interval, okay? So the average rate of change is no more than the slope of the secant line through 2 points, and it's very important that we know this formula here. Cheers.